Welcome to the Crazy Hat Chemist. So another video here on acids, bases, and titration. So let's get moving. Bam! So today we are talking about a weak base calculation number 2. All right, let me read the question for you here. It says, determine the equilibrium concentrations of all species of a 0.25 molar ammonia solution. Then we're going to determine the pH. The Kb for the ammonia is 1.8 times 10 to the negative 5. We're also going to get the percent ionization or percent dissociation here at the very end here as well. All right, so let's get moving. So we're going to write the reactants plus ammonia, that is writing ammonia plus water. So ammonia is NH3. We're going to write water as H2O or HOH. It really doesn't matter. So that's what I got right there. And I got ammonia as NH3, that is aqueous. And I got the water, and that's a liquid. Again, we're talking about water as a liquid. That's very important. Okay, now in order to write the products, we're going to consider the conjugate pairs of the reactants. We do know that ammonia is a base. It has a Kb value. Being that it is a base, it produces hydroxide ions. Therefore, we know the conjugate to the water, and that conjugate would be hydroxide. Therefore, the water is losing a hydrogen. And that hydrogen is going where? That hydrogen is attaching to the ammonia. And then the ammonia, which is a base, needs a conjugate acid. Its conjugate acid is the ammonium ion. Okay, so this is how we come up with the products. We get the conjugate pairs of the reactants. Writing the reactant side with the water really truly helps us out so that we can get the conjugate pairs. Ammonia, NH3, is a base. We need to write its conjugate acid. That's an addition of a hydrogen ion. That gives me NH4 1+. The conjugate for water that's on the reactant side is hydroxide or hydronium ion. But since this is a base, then it produces hydroxide ion. Okay? Now that we have the balanced equation here with our reactants and our products, then what we need to do this mathematically is we are going to use what's called an ice table. And hopefully you remember way back, not too far long ago really, but way back to the equilibrium unit. And we started off with ice tables there. And an ice table is the initial, the change, and the equilibrium set. So initially, what we have on this problem is 0.25 molar ammonia. So I'm going to place that right where the ammonia is initially. Initially, how much water do I have? Well, it really doesn't matter because water is a liquid, and liquids are not included in K expressions of any kind. So that's why I'm going to delete that and not, or ignore it, if you will. Now, in order to get the products here, I'm going to ask myself, well, this is an initial set of data here. And since it's an initial set of data, this reaction actually has not started. Therefore, I don't have anything for either of the products. So therefore, for the ammonium ion, I'm going to place a 0. For the hydroxide ion, I'm going to place a 0. Okay, now the change. The change column is that I am going to decrease the amount of reactants because the reactants are going to go from reactants to products. So therefore, the reactants will decrease. Now, I'm also going to use the stoichiometric coefficients on the reactants, and that is a 1 stoichiometric coefficient in front of ammonia. So therefore, it's going to be a minus 1x. So that's why I have that right there. Again, the water, since it's a liquid, I'm going to ignore that. Now I'm going to deal with the products. The products are going to be produced. That means that they are going to increase. Well, they actually started off with 0, so you have nowhere to go but to increase. Both of the products, that is the ammonium ion and the hydroxide ion, both have a stoichiometric coefficient of a 1. Therefore, it's going to be a plus 1x for both the ammonium ion and a plus 1x for the hydroxide ion. Now, in order to get the equilibrium data set, I have the initial, I have the change. I'm going to add up the initial column and the change column, and I'm going to get the equilibrium column. So for the ammonia, I'm going to have 0.25 minus x. For the water, I'm going to have nothing again. And then for the ammonium ion, it's 0 plus x, that's x, and the hydroxide is 0 plus x, that is x. Okay, now at this point in time, now we're going to write the Kb expression. So that's products over reactants with the stoichiometric coefficients as exponents. Solids and liquids are not included. I do have a liquid here, and that is certainly not included. So the Kb is equal to the ammonium ion in the numerator, the hydroxide ion in the numerator. These are both in brackets with exponents of 1 for both of them. And then in the denominator, I have ammonia, and that's also in brackets with the exponent of a 1. Okay, the water is not included because the liquids are not included in any K expression. So now what I'm going to do is I'm going to take that Kb expression that I have and substitute in the information from the equilibrium set as well as the Kb itself that was given to me in the problem. Okay, so I'm going to substitute into this equation. So now on the left-hand side of this, I have 1.8 times 10 to the negative 5. On the right-hand side, in the numerator term, I have x times x. In the denominator term, I have 0.25 minus x. Now I'm going to ask myself this question here, and I keep on asking myself this question, and that is 100 times the k. The k happens to be 1.8 times 10 to the negative 5. Is that less than the initial concentration, which in this case is 0.25? So if that is true, and which it is, then I can use the approximation to the quadratic equation. And if that is true, then the approximation works, and therefore, how do I use this approximation and apply it? I'm going to get rid of that minus x term in the denominator. Okay. So now what I'm going to do is take my 1.8 times 10 to the negative 5, that's on my left-hand side. My numerator term is going to be x squared, and my denominator term is just going to be 0.25 without the minus x. And that's what I have right there. All right, so now what we're going to do is we're going to solve this for x. So I got 1.8 times 10 to the negative 5. I'm going to multiply that by 0.25. I'm going to take the square root of that, and then I'm going to get this value here, and that is solving for x. X is equal to 2.1 times 10 to the negative 3. So now what we're going to do is look in the equilibrium set of data. That's where I have that blue dashed line, and I'm going to solve for the ammonia concentration, the ammonium ion concentration, and the hydroxide ion concentration. And then after that, then I'm going to work on the pH. So for the ammonia concentration, it is 0.25 minus x. X is 2.1 times 10 to the negative 3. I'm going to do that subtraction. In my calculator, I get the value of 0.2479. But using significant figures, of which there are 2 here in this problem here, or 2 decimal places, since I am doing a subtraction problem, this is 2 decimal places. My number is 0.25 molar for the ammonia. Again, this should reconfirm to you that the minus x term that you got rid of is okay, and that is that the value for x is so small compared to the initial concentration that it has no effect on it. All right, fantastic. All right, now we're going to get the ammonium ion concentration, which is 2.1 times 10 to the negative 3 molar. And then we're going to get the hydroxide ion concentration, which is 2.1 times 10 to the negative 3 molar. So both the ammonium ion and the hydroxide ion concentration are equal to x, and that's why those values are 2.1 times 10 to the negative 3 molar. Okay, now the next thing that we need to do is we need to solve for the pH. And the last, or the previous problem, I used the Kw is equal to the hydroxide times the hydronium ion, and that's equal to 1 times 10 to the negative 14. This time I'm going to use something different. I'm going to get the POH, and that's taking the negative log of the hydroxide ion concentration, and that will give me the POH. So POH is equal to the negative log of 2.1 times 10 to the negative 3. That's going to give me a value of the POH as 2.68. So now that I have a value of 2.68 for the POH, now I know the other mathematical equation, which is pH plus POH is equal to 14.00. And so I'm going to plug into that equation right here. pH plus 2.68 is equal to 14.00. I'm going to subtract 2.68 on both sides. I'm going to get the pH. The pH here is 11.32. And again, I want you to always be thinking about, do the numbers make sense? Okay, so don't just blindly calculate values and plug it in and then solve for it and then be done with the problem. You really need to be thinking about, does this number make sense? Now, ammonia is a base. It's a weak base, and it therefore should have a pH that is greater than 7. Okay, and is this pH greater than 7? It's 11.32. It absolutely is greater than 7. So that number should make sense. Okay, Also, just to reiterate here, there are rules for logs and natural logs in determining the number of significant figures, but for pHs we're going to have 2 decimal places, and that's why that pH is 11.32 and not some other value of 11.3, for example. Okay, we got one more thing here to do on this problem here, and that is to solve for the percent ionization. Now, since it is a weak base, I know that the percent ionization is certainly less than 100%, because that's one of the definitions. It's that strong acids and strong bases dissociate or ionize 100%, and the weak ones do something less than 100%. So what we're going to do is, to get the percent ionization, is we're going to take the value for X, and then we're going to divide that by the initial concentration. We're going to multiply that by 100 because I want a percentage. So here on the top here is this percent ionization. I got 2.1 times 10 to the negative 3 divided by 0.25. I'm going to take the quotient, that is, divide those two numbers, and then multiply that by 100, and I am going to get this value right here, which is 0.84%. So that is ammonia under these conditions here of 0.25 molar only dissociates 0.84%. That is certainly less than 100%, and that also makes sense because it's a weak base. Okay, I'm the Crazy Hat Chemist, and I got a great crazy hat here for you. Okay, so what am I is the question. Am I an onion? No, I am a garlic clove. So, like that hat, give me a thumbs up, subscribe to my YouTube channel, pass on my YouTube channel to everyone you know. Okay, and please subscribe to my YouTube channel. Look at my website. There's lots of great videos and information on the website as well, and please donate. Thank you very much, and I'll see you next time for more cool chemistry videos. Bye for now.